Okay, let's dive into this. When you really stop and think about transporting massive quantities of volatile liquefied gases across the world's oceans, the sheer engineering required is almost hard to comprehend. We're literally talking about packaging highly pressurized or deeply frozen cryogenics inside massive floating steel structures. So today, in this explainer, we are going to unpack the incredible containment architecture of gas carriers. We'll start right at the cargo tank itself and slowly zoom all the way out, looking at the strict rules of physics they have to obey and the legal structures that mandate exactly how they're built to keep us all safe. Here's our inside-out roadmap for today. We'll kick things off with membrane versus independent tanks. Then we'll break down the independent tank types, look at how they survive shrinkage and flooding, explore the secondary barrier rule, and finally wrap up with hazard levels and ship classes. All right, Section 1, membrane versus independent tanks. Two totally opposite engineering philosophies. You know, two gas carriers can look absolutely identical from the dock, but they might carry their cargo in fundamentally different ways deep inside their hulls. On one hand, we have membrane tanks. The walls on these are incredibly thin, like literally a couple of millimeters thick, almost paper thin when you're talking about heavy industry. They hold the liquid's pressure and create a leak-tight seal, but the actual structural load, that passes straight through the insulation and right into the ship's own hull. The hull does the heavy lifting. You've got Gas Transport's INVAR system, which uses a special nickel-steel alloy that barely expands, and Technogaz's Mark III corrugated stainless steel. Both were massive competitors, though they've actually merged into a company called GTT now. On the flip side, you have independent tanks. These are fully self-supporting freestanding structures sitting right inside a hold space. They do not rely on the hull for structural support. But because you're basically building an entire second structure inside the ship, it's going to cost you a lot more in terms of steel and space. Now, there's also a middle path here, the semi-membrane tank. It's definitely less common, but it exists to split the difference. The flat sections act just like a membrane, leaning on the ship's hull for support, while the curved corners are totally rigid and self-supporting, just like an independent tank. It's a really clever hybrid compromise, mostly used for specific cargoes or unique hull shapes where a pure membrane design just wouldn't fit right. Let's do a really quick check to make sure we've got this core concept down. In a membrane tank, what actually carries the cargo's structural load? Is it the tank wall or the hull? Yup, it's the hull. That paper-thin membrane merely holds the pressure. The heavy lifting is handled entirely by the ship's outer steel structure. Moving on to Section 2, independent tank types, specifically the legal subtypes A, B, and C. So the term independent isn't just one single design. It branches into 3 distinct legal subtypes based on how rigorous the engineering and safety backup requirements are. Now, what's really interesting about this slide is seeing how the math dictates the safety gear. Take type A. It's engineered using classical analysis, meaning it can't mathematically rule out a crock spreading. Because of that uncertainty, the rules mandate a full secondary barrier, a complete backup that could hold all the cargo if things go wrong. Then you have type B. These are engineered using highly rigorous advanced fracture mechanics. Because engineers can mathematically prove exactly how and where a crack would form before it fails completely, the rules relax a bit. Type B only needs a partial secondary barrier, like a drip tray. Those famous Moss spherical tanks, those are type B. And finally, type C. These are basically massive, thick-walled pressure vessels. Their safety margin is baked directly into their extreme pressure ratings, often 17 to 18 bar, so they require 0 secondary barrier at all. So, let's lock this in. Which independent tank type requires 0 secondary barrier at all? Exactly, type C. Because it's built to incredibly strict pressure vessel codes, the sheer thickness of the metal itself acts as the failsafe. No physical backup required. All right, Section 3, surviving shrinkage and flooding. Let's talk about the physical supports. So picking your tank type is just step 1. Now you have to actually mount this colossal structure inside a ship that's moving on the ocean. And here's the catch. Cooling a massive steel structure down to minus 104 degrees Celsius, or minus 162 for LNG, means the tank physically shrinks. A lot. So engineers are faced with a massive contradiction. You have to hold the tank rigidly enough so it doesn't smash around when the ship is pitching and rolling in rough seas. But if you bolt it down completely rigid, it'll literally tear itself apart as it shrinks during cooldown. The ingenious solution? Cradles and keyways. Keyways are these slotted supports that hold the tank incredibly tight against side-to-side motion, but they let it slide lengthwise as it contracts and expands. It's brilliant. But wait, there is another, frankly terrifying scenario. Imagine the hold space around an independent tank floods because of a hull breach. An empty or even lightly loaded gas tank is insanely buoyant. It would literally pop up and float inside the ship, ripping right through its piping and structural connections. Just a complete disaster. To stop this from ever happening, they use anti-float brackets. These are welded right over the top of the tank to physically lock it down against that incredible upward force of buoyancy. Time for another quick check. Why can't an independent tank just be bolted rigidly to its supports in every direction? Right, because of thermal contraction. The freezing cargo causes the tank to physically shrink. If it was bolted down tight, that shrinkage would fight against the mounts, shooting massive stress right into the tank shell and causing a structural failure. Which brings us to Section 4, the secondary barrier rule. What happens when the primary fails? Okay, so the supports did their job, but the worst happens. The primary tank springs a leak. What now? Well, your very first line of defense is the environment directly around the tank, called the hold space. And this isn't just a pocket of empty dead air. It is a highly controlled, actively monitored gap filled with dry air or inert gas. This space is absolutely packed with sensors designed to catch the very first microscopic trace of a leak, way before it turns into a visible emergency on deck. And if a leak is detected, a very specific clock starts ticking. 15 days. By international code, a secondary barrier, whether that's the full backup tank on a Type A or the drip tray on a Type B, has to be engineered to hold that leaking cryogenic liquid for exactly 15 days. Now, that's not just a random number they pulled out of a hat. That is the mathematically calculated maximum time it would take for a vessel stranded in the middle of the ocean to safely divert and reach a specialized repair port. And if that freezing liquid cargo actually touches the ship's hull, we've got a major materials crisis on our hands. See, ordinary, mild ship steel becomes violently brittle at those temperatures. It can literally shatter like glass. Because of that catastrophic risk, any hull structure that might realistically be exposed to a leak has to be built with special temperature-rated steel. You can't just build for normal operations. You absolutely have to build the ship to survive the worst-case emergency temperatures. Finally, Section 5. Hazard levels and ship classes, the full classification ladder. So stepping back and looking at the entire vessel, the actual chemical hazard of the cargo is what dictates the physical architecture of the whole ship. A Type 1G ship carries maximum hazard cargo, stuff like highly toxic chlorine. Because a leak would be devastating, 1G tanks must be placed the deepest inboard, meaning there has to be a minimum clearance of 1/5 of the ship's total breadth from the outer hull. That's so they can survive a massive collision without breaching. Then you have Type 2G and 2PG ships. These handle moderate hazards like LNG and ammonia, so the rules allow for slightly more relaxed tank placement. And at the bottom of the ladder, Type 3G ships carry the least hazardous cargoes, like LPG, giving engineers the maximum amount of flexibility in cargo volume. Now, besides hazard placement, ships are also classed by how they manage the gas itself. Fully pressurized carriers just let the pressure naturally rise to 17 or 18 bar at ambient temperatures. It's the simplest design, using those heavy Type C tanks with zero cooling needed. Then you have semi-pressurized carriers. These strike a middle ground. They use partial cooling to drop the pressure to around 5 to 7 bar. That allows for thinner, lighter tanks without needing a massive cooling plant. Lastly, we have fully refrigerated carriers. These keep the cargo chilled right down near its boiling point at just 0.25 bar of pressure. But to do that, you need giant insulated tanks and a full, continuously running onboard refrigeration plant. It's an incredible commercial and technical balancing act between tank thickness, refrigeration costs, and cargo volume. Let's make sure this is crystal clear before we wrap up. Which carrier class needs a full onboard refrigeration plant to keep the cargo near its boiling point at low pressure? Yep, the fully refrigerated class. They absolutely rely on active mechanical cooling to remove the heat that naturally leaks in, keeping the pressure safely near atmospheric levels. So we've gone all the way from the paper-thin membranes holding pressure inside the hull to the intense 15-day survival clocks right out to the massive collision clearances of the outer steel. It's an engineering marvel. But it leaves us with an incredibly provocative question. As the world shifts toward new experimental liquid fuels, how is this extreme engineering going to evolve? What on earth will the gas carriers of tomorrow look like? Thank you so much for joining me on this explainer. I hope you found it as fascinating as I do.